Hi, I'm Claire Dorman. I'm a grad student here at UCSC. And I'm going to tell you about the age dispersion correlation that we're seeing in Andromeda's stellar disk. So, like Colin, I would like to know what processes impacted the formation and evolution of large stellar disks and galaxies like the Milky Way. Ideally, we'd like to be able to split a stellar disk up into stars of different ages and map their vertical structure, or equivalently, their velocity dispersion, map some measure of the heating to figure out what processes were influencing the disk at different points in the galaxy's history. Turns out this is actually pretty hard to do. There are many great attempts. On the kinematic side, we have some very detailed data of the Milky Way, but our view of the disk is limited to the solar neighborhood, and so we have no way of knowing if the measurements that we're taking here are representative of what's going on over the entire disk. If you look at more distant galaxies, you can get integrated light spectra to get kinematics over an entire galaxy, but your spectra will include contributions of light from stars of different ages. So you're not really able to map a time series of what's happening in the disk. You can also map the scale height of a galaxy. There's been some nice work done with resolved stellar photometry of relatively nearby galaxies. So you can use photometry to separate out stars of different ages, and if the galaxy happens to be edge-on, then you can map the scale heights. But you have a similar problem here as in the Milky Way, where because the galaxy is edge-on, you don't have a great view of what's happening over the entire disk. So fortunately, there is a Goldilocks galaxy. It is at M31. Andromeda is ideal for studying age trends in large disks like this. It's a large spiral. It's an analog to the Milky Way. It's nearby enough that we can get velocities of individual stars. And it is oriented outside of us and oriented such that we have an unobstructed view of an entire side of the disk. So I'm going to tell you about mapping the velocity dispersion in M31's disk separately for stars in 4 different age bins. We have some fantastic data sets to do this. The first is the Panchromatic Hubble Andromeda Treasury Program, FAT, with which you've already heard about twice today. This is our recently completed multi-year Hubble photometry program. It images a third of Andromeda's disk, and so we now have 6-filter Hubble photometry of 100 million individual stars. So that's pretty useful. And at Santa Cruz, we've been supplementing this with the SPLASH survey. That's the regions shown in pink here. We've been using DEIMOS on Keck to get spectra and thus measure radial velocities of thousands of the same stars that were surveyed with FAT. So we now have photometry and kinematics of a lot of stars in the crowded disk of Andromeda. So what do we do with these? The first step is to split the spectroscopic sample into 4 different age bins, and we do this using the FAT photometry. So here's an optical color magnitude diagram of stars in M31. This is working? Yes. So this is from FAT. This is essentially I versus B minus I. And up at the bright end here, you can see the massive main sequence. So these are stars above several solar masses. They're very young. And then coming off to the right is the old red giant branch. And brighter than the tip of the red giant branch, you can see asymptotic giant branch stars, which have a range of ages but will be intermediate between these 2 populations. So the green region here shows where we can get spectra. So now I'm going to zoom in on that region and show you stars that we do have spectra of. Again, you can see the young massive main sequence, the red giant branch, and then the asymptotic giant branch. So I'm using this to split my stars into 4 age bins. Main sequence are the youngest, and then younger AGB, then older AGB, and our red giants are our oldest on average. Now, of course, these regions will have overlap in age. All I'm trying to do is separate them into stars that have different average ages. And to estimate their ages, we've used a constant star formation rate to generate a really, really simple simulated CMD and split those stars into the same 4 age bins, just to get a rough idea of what these ages might be. And indeed, the average ages of our populations are increasing, from 100 megayears for the main sequence stars to a couple to several gigayears for our red giant stars. So now going back to the real data, we now map the velocity dispersion for stars in each age bin. And I'm just going to give you an example using the red giant stars. So this is a map, just an RA and DEC space of our spectroscopic targets that are red giants. The center of the galaxy is right here, where this half cut off X is. The dots are color-coded here by velocity, so red stars are red-shifted away from you, blue stars are blue-shifted towards you. And so for each of these stars, I get a velocity dispersion by grabbing all the neighbors within some radius, calculating the velocity dispersion, do that for every single star, and you end up with a map. So this is a map of the velocity dispersion. I want you to take a look at the scale, because it's going to be the same in all the rest of the plots that I show you. Black is 15 kilometers per second. That's very thin. That's dynamically cold. The scale goes all the way up to 150 kilometers per second. That's very dynamically hot. For reference, the oldest, thickest stars in the Milky Way's disk have a dispersion of about 50 kilometers per second. So we're talking pretty hot here. So we can do this for each of our 4 age bins, and I'm just going to flip through them now, and notice that the average dispersion is increasing. Here are our youngest stars. This is the main sequence bin, pretty cold. Go up 1 age bin, colors are getting lighter, dispersion's going up. 1 more age bin, dispersion's going up a little bit more. And if we get to our oldest age bin, we have really, really high dispersions for the red giant stars. I can put all of those 4 maps together. This is just a compilation of the 4 that I've just showed you. Each line is the dispersion distribution for the stars in 1 age bin. So again, you can see there's this monotonic increase in typical dispersion with typical age. From the main sequence to younger AGB, older AGB is about 80 kilometers per second, and red giants about 90 to 100 kilometers per second. So this is pretty interesting. It shows that there's some continuous heating or cooling process that has been happening all throughout the galaxy's history. It's not like all stars below some age range have some cold dispersion, and all stars above that have some hot dispersion. Okay, that could happen if there were maybe one accretion event that were creating all of the dynamically hot stars. We don't see that, so some continuous process has been happening. Here we can get a tiny bit more quantitative. I'm showing the mean dispersion from our age bins versus that age that we estimated very heuristically from that simulated CMD. And then for comparison, I'm also showing the same data from the solar neighborhood in the Milky Way. And even if you don't believe our ages, which you shouldn't, you can very clearly say that the heating rate in M31, the slope of that black line, is much, much higher than the heating rate in in the Milky Way. So at any given age, you've got a much higher dispersion pretty much than anywhere in the Milky Way. Okay, so that's pretty interesting. That implies that M31 has had a more active history than the Milky Way, maybe through more satellite impacts that have disrupted the disk. That's the same trend that we see in the halos. There's a lot more satellite debris in the halo of M31 than there is in the halo of the Milky Way. So that's not particularly surprising, but it is a nice striking result. The last thing I want to show you is that the stars in all of our age bins are kinematically clumpy. And by this I mean that the dispersion map for each of our bins is patchy. There's contiguous patches that have high and low dispersion. It's easiest to see that in the red giant branch map, in the old map, because we have so many stars there, but it's present in all of the maps. So one of the features that is easiest to see, and is interesting because it's present in all bins, is this one right here. It's a dynamically hot patch on the major axis of the galaxy. Again, this is the center of the galaxy. And for reference, I have a Herschel image of the same portion of the galaxy. So this corresponds with the inner ring and also probably with the end of the long bar. But anyway, so you can see it clearly here, a hot patch in the red giants. I'm going to flip through the stars again, this time going younger. So if we go 1 younger, that patch is still there, even though the overall dispersion has decreased. Go down 1 more, it's still there. And even in the main sequence stars, it's a little bit less obvious, but there are still some dynamically hotter regions in there. So I'm not going to tell you exactly what's happening here because I don't know, but one interesting thought is that it could be the dynamical signature of the end of the long bar. So Leah Fanasula has done some simulations that show that the bar in M31, the boxy part of the bulge is pretty short, but it looks like there's a long bar that goes out pretty much to where this hot patch is. So if you imagine that stars in a bar have X-shaped orbits, very different orbits from the circular orbits of stars that are in a disk. So if you look at one region of the sky here, near the end of the bar, you're going to have some stars that have bar-like orbits and some stars that have disk-like orbits. So that's a large spread in velocities. So if you calculate the dispersion of those stars, you're going to get an inflated number. You're going to get a really high number. And because we see this in all 4 of our age bins, I think it's interesting to think that this might be what's happening. But there are, of course, a lot of other options, including maybe a very recent satellite impact that's had an effect on all of the stars, no matter how young they are. So that's all I have to say. In summary, we've seen a clean monotonic age dispersion correlation in stars in the stellar disk. We've seen a clumpy dispersion map for all ages, and high overall dispersion and heating rate compared to what we see in the Milky Way. Thank you. Sure. Yes, I'm flippantly using the word heating here to refer to the slope of the dispersion to age line. It could be a heating process. It could also be stars forming in a thicker gas disk that then cools and forms younger stars in thinner layers. That could absolutely be happening. Probably some combination, yes. I do. Yeah, so if you estimate photometric metallicity using the optical CMD and split the red giant stars into low metallicity and high metallicity bins, and then make dispersion maps for those 2 bins, the metal-rich stars are colder, and the metal-poor stars are dynamically hotter. And I did not plant that question with Raja. I just happened to have the backup slides. But that's all the backup slides I have. Yes.
The velocity range is much higher than disk stars. So I wonder if they could be disk stars or so maybe here, but the halo stars or so that. Yeah. Anyway, so.
Yeah.
Are these disk stars?
That's a very good question, and that kind of gets to the definition of what you mean by halo. So if you do, in my last paper, we did a structural decomposition, including the surface brightness and the kinematics and the luminosity function, and there's an excess of dynamically hot stars above what you can account for using just the disk surface brightness. But there are also a bunch of simulations that show that if you have a satellite impact coming in to an originally cold disk, you can kick stars up such that they have halo-like kinematics. So these stars appear to have a disk-like surface brightness profile, but halo-like kinematics. And so you can call those halo if you want. It's unclear exactly where they belong, but they appear to have a disk-like surface brightness profile and luminosity function. So it's very, very high dispersion. So yeah, definitely open to more suggestions because they are very hot. Yes, sure.
More questions to Claire? Yeah.
Just to emphasize, so I mean, Julianne Buchanan has done, from her dust maps, she's managed to work out the thickness of the RGB, of the main part of the RGB disk. It's about a kiloparsec thick, which is much thicker than the thick. I mean, it's about the same thickness as the thickness of our Milky Way. That's the main disk of M31. So M31 itself is kind of quite a different beast in terms of disk properties to that. That's
absolutely.
Cold population.
It probably is. Probably is. Yes.
So let's thank Claire again then and all the speakers on the And actually we do have some time scheduled for discussion unless people want to run away. The problem is that we started with the cold stream and the angular momentum history and distributions, and indeed we have
to get kinematics over an entire galaxy. But your spectra will include contributions of light from stars of different ages. So you're not really able to map a time series of what's happening in the disk. You can also map the scale height of a galaxy. Hi, I'm Claire Dorman. I'm a grad student here at UCSC. And I'm going to tell you about the age dispersion correlation that we're seeing in Andromedas of different ages and map their vertical structure, or equivalently their velocity dispersion, map some measure of the heating to figure out what processes were influencing the disk at different points in the galaxy's history. Turns out this is actually pretty hard to do. There are many great attempts at a stellar disk. So, like Colin, I would like to know what processes impacted the formation and evolution of large stellar disks and galaxies like the Milky Way. Ideally, we'd like to be able to split a stellar disk up into stars. On the kinematic side, we have some very detailed data of the Milky Way, but our view of the disk is limited to the solar neighborhood, and so we have no way of knowing if the measurements that we're taking here are representative of what's going on over the entire disk. If you look at more distant galaxies, you can get integrated light spectra.